Hello everyone, welcome back to the next practice session in the subject of division in multi-component solids. And this is a week 3 that we are conducting an online practice session. Online practice session that we are conducting right now. So in this week, we will be solving some of the concept, and we will be discussing a brief uh, discussion on the topics that we have already taught by the last week, that is in week 3. So this will be helpful for the recapping of or recalling the concept in the present in diffusion. And just we are just entering into the concept of diffusion in the after the first week and second week, that is a refreshment of thermodynamics, that will give a brief introduction to the thermodynamics of material that will help for understanding the diffusion concepts in the upcoming weeks. So in this week we will be understanding some of the concept, as well as 3 to 4 problems or numericals which is practically used in the field, practically used in the other fields, how that this diffusion will help in the other fields also. So we will understand in this week. Okay, so we'll wait for 1 to 2 minutes. Let us start our week 3 session. Okay. Okay. So welcome to the next practice session, diffusion in multi-component solids. So this is the content of week 3. So we will be just starting the contents of week 3. So just brief, we will brush up all the concept that been explained in the week 3. Then we will go into the problems one by one. So that will be helpful for solving the some concept oriented questions. So in this one, the exercise of a solution thermodynamics is in this one, the first question so that has been explained is the other form of enthalpy of mixing for regular solution, delta Hm, that will be equal to RT into summation of xi. Sorry, here I will write it one more time. So delta H M regular solution will be equal to RT into summation of Xi ln of gamma I. That means an activity coefficient. This is the correct answer for the expressing, and the how it has been derived is explained in the video completely. This will be used for the other numericals also. And again, the second question, they have calculated the activity coefficient of any component gamma. That can be determined with help of a basic equation, delta G A into equal to RT ln gamma A. Okay, so that will be gamma A. From here, we can write it as RT into ln XA plus RT into, here it is A of activity of A component. So we know activity of A component equal to gamma into X, gamma into Xi. That can be written as Xa into RT into ln of gamma I, right? So from here, so we will be determining the activity coefficient, that is gamma of A component. After that, so we will be determining the enthalpy of mixing when when there is a sequence of process in it, from A to B, B to C. So last question is about fourth question, that is in the phase diagram. Any of the phase diagram, what how we will be drawing G versus X graphs. That I have explained in the previously. So can you tell me which type of, this I have to write it one more time. So can you tell me which type of graph it is, which type of phase diagram? Yeah, it is a eutectic type of phase diagram. This is alpha and this is liquid, alpha plus liquid, and this is beta. Okay, this is alpha plus beta. One thing that we can observe in all the phase diagram, so when you travel, when you keep the temperature as constant, and this is composition. So one thing that we are observed here is when you temperature is constant, when you're traveling from left to right hand towards this side, you will get single phase plus double phase plus single phase. This is in the binary case. See here, for example, this is the, so in this case, this is the one temperature that I am traveling. So it is started with alpha single phase, alpha plus beta here, alpha plus beta, again it is beta. See, single phase, dual phase, single phase. This is a property of a phase diagram that we are observed. So here we can draw at this temperature. Can we draw the G versus X graph? It's very easy. Yes. So first we will draw. So G versus X. This is X1 and this is X2. Okay, and this is liquid. So here there are three phases: alpha, beta, and liquid. Three phases are there, right? So alpha plus beta, and beta, whereas liquid. But this is not another phase, but we have different three phases, combination of these two phases only. So for that case, up to x1, so just note down the x1 and x2 here. This is x1 and this is x2. Up to x1, gamma is stable. After, in between x1 and x2, alpha plus beta both are stable, whereas in x2, the after x2, beta is stable. How we will be drawing this one? Let us see. So for example, this is the curve. Here is it. So this is for hey, sorry. Okay, so somewhere here it is there liquid. It is not a stable at all at this temperature. That's why. So when you draw a common tangent, so this one will be the your x1. Sorry for this one. I will write it one more time. Here it is there, and here it is x1, and here it is x2. So up to here it is alpha is stable, and here it is beta is stable. Here it is alpha plus beta is stable, right? Okay. So this is how we will be drawing a G versus. Oh, sorry, I have to write it. Here it is G. G versus X composition graph, Gibbs energy versus composition graph with the help of phase diagram. In actual cases, what we will be doing, so we are plotting, we are getting this phase diagrams with help of this G versus X graph. But in our case, for learning purposes, we are getting phase diagram into G versus X graph. But in real case, what will happen is we will be getting this graph at this temperature, and then we will be drawing this phase diagram. So for that one, we will be conducting a series of experiments at a various temperatures. Then we will plot a G versus X graph for every temperature. Then we will plot into this phase diagram. Then we will get a phase diagram for each component. Yes. Yeah. So this is that we have learned in the lecture 10. After that, in lecture 11, there is a concept of a driving force, chemical potential, and concentrations. So driving force is related to the activation energy. This is a theory of. So here the two or three more concepts will be there. What is the stable state? What is metastable state? Metastable state. So a stable state, it's having a lowest energy. That means it is satisfied everything and it is stable one. So no one can make any changes in this one. Whereas metastable, as the name indicates, meta stable. So we can understand this concept with this diagram itself as explained in the lecture series. Yeah. So this is the energy level EA, and this is the atomic position. Okay. So this is the minimum level that we have right now. Okay, and this is a higher energy level, and this is the minimum energy level. So this is considered as stable state, and this is considered as metastable state. So we can have only one stable state in a system. We should have one stable state, and but we can have multiple metastable state. Just we are comparing with this high energy level to the this lower energy level, then we can say this is a meta. But out of this metastable state, one energy state will be a lowest energy level, that is called stable state. This is how we will be differentiating metastable state as well as stable state. And from here it is rate into is equals to directly proportional to exponential of Arrhenius kind of equations that we get right now here, Ga into R into T. This is by the theory of kinetics. Yes, by theory of kinetics. So this can be explained with the help of a movement of the atoms in the interstitial sites as well as in the atomic positions. Everything that is explained here. After that, the conversion of concentration is also explained in this video. That is mole fraction, weight fraction, so volume fraction. All the things is explained. How we will be converting, and then converting from Ci to Xi. There is a mole fraction. Yes. absolute the concentration to the mole fraction. Right? So after that, uh, we will be discussing about diffusion, flux, and the flux frame of references. This is very important concept, frame of references, that we need to take care about everything here concept wise. So first, the term has been explained. What is diffusion flux? So what is diffusion flux? J. So its unit mole per meter square second or meter cube per meter square per second. And how this Fix has started his first experiment is also explained. Oh, sorry, it's explained in the next video lecture. The concentration is equals to number of atoms that is traveling per unit area per unit time. Concentration flux. Concentration of the ith component, and it is related to the diffusion flux. Flux is equals to that concentration into velocity of that component, right? Concentration of I to the velocity of I. So in the frame of references, so first explain the volume fixed frame of reference. Volume fixed frame of references. B. Mass fixed frame of reference. C. Molar fixed. So yes, mole fixed frame of reference. In each frame of references, we will be calculating the velocity. So in the volume fixed frame of reference, velocity is equal to summation of yes. So this is the thing, and that is UV is equals to uh, molar volume into flux of I component. Molar volume of I component to the molar volume flux of I component. Whereas in the second mass spectral frame of reference, velocity is equals to so summation of Ji Mi to density. Whereas sixth component Of so what the mole fixed frame of reference, molar volume to the flux of J. So these are all the things that need to think about. So here, oh sorry. So this is covered in this one. And next is in lecture 13, explained about the how this fix carried out the experiment to demonstrate his first law, that is steady state diffusion flux, which is, and we have also explained the in the video, which it is analogous to the other two things also, Fourier and Ohms. Okay, so he has conducted his experiment with a salt water, with a pure water salt reservoir along with the against the pure water, and he had considered this as a steady state condition, and he come into existence of in the presence of an external driving force. We can write it J is equals to minus d dou c by dou x plus c into, this is in the presence of, this is a drift term comes into exist. So last is exercise of deriving a sigma cosine for the any cubic lattices. For a simple cubic, any cubic lattices, summation of square theta I is equals to 6 by 3, that is z by 3. In general, he has derived, that is, it is for any simple cube, any cubic system, it is equals to z by 3. And then last, okay, so in this video lecture, explained about only about the cosine for the cubic lattices. Again, in the upcoming videos, we will be jumping into the hardcore diffusion concepts. So how this Fick's law is applicable for the multi-component systems such as ternary system. It's only applicable, so it's when it is in comparison with the alloys, how it will be used for binary, ternary, and quaternary, and so on. So we will be deriving this equation for the ternary and quaternary system. So let's jump into the questions. So if you have any doubts, please let me know. Before getting into the numericals for today's sessions, so I will be explaining one concept regarding with frame of references. So different frame of reference, I will little bit try to explain those things. So I think most of will get confused regarding with the frame of references. So understanding all those things. So volume, frame of reference. So volume fixed frame of reference. Frame of reference. First thing, so we will write the definition first, then we will jump into the its meaning. Fixed on local, fixed on local, local center of volume of all components then the net flux expressed expressed in terms of volume is zero. So what is the meaning of this one? Fixed on local center of volume at all the components of all the components, the net flux expressed in terms of volume is zero. Okay. So from definition, we can say partial molar volume into its flux with respect to volume is zero. So if you consider a diffusion couple, this is A and this is B. If an atom, it is a VA partial molar and this is VB partial molar volume that VA has. So VA is greater than VB. So when the atom is jumping from here to here, the molar volume of this component will changes. So from here to here, whether it will change, whether changes or not, yes, it is changes. Whether it is increases or decreases, yes, it is increases because it is the molar volume of this component is higher than this one and it is moving towards this side, this initial joint. Okay, this is a basic concept behind the molar volume fixed frame of reference, a volume of the component, but we are considering a volume as constant. Partial molar volume after this one is constant. So mass fixed frame of reference, mass fixed frame. Here, similarly, fixed on local center of mass of all the components, the net flux expressed in terms of mass is zero. Fixed on local center of mass of all component, net flux expressed in terms of mass is 0. That means summation of JIM into molar mass is equals to partial molar of mass. Partial molar mass is 0. So this is explained in the mass fixed frame of reference. In third, mole fixed frame of reference, mole fixed frame of reference fixed on local center of moles. Here we are considering the number of moles are fixed on the local center of mole of all the components. The net flux expressed in terms of its mole is 0. The expression will be like this. So one more frame of references that is not mentioned in this video, that is lattice fixed frame of reference. Lattice fixed frame of reference. This is also called as Kindle frame of references. Kindle okay. So this is all about the frame of references that been used in the explaining the concept of diffusion. Okay, so let's jump into the problem session. So today's first problem is related to the diffusion in the gloves that we have. Here, the sentence first I will read it. The methyl chloride is a common ingredient of a paint of paint removers. This, besides being an irritant, it also may be absorbed through the skin. When using this paint remover, the protective gloves should be worn. A methyl chloride is a paint removal of liquid which used to remove all the paints. Okay, so this may cause irritation to your skin. This irritation because of its diffusing property into the skin. So then, if a butyl rubber gloves have been used of 0.04 mm thickness, C, are used, what is a diffusion flux of a methyl chloride to the gloves? So we need to determine the diffusion flux, how much it is diffusing. So assuming there is a steady state condition, so before that one, so what do you mean by steady state? First thing, what is mean by steady state? Let us try to understand this. Steady state means if you analyze, so this is a diffusing path. Assume I have made 3 points. Okay, so this is within the diffusion zone, I'm saying. Okay, so if you measure the concentration in the x1 position, in x2 position, in x3 position, after time interval of 10 minutes, 20 minutes, 30 minutes, 40 minutes, this concentration should remain constant. C1, C2, C3. That is nothing but a steady state. Concentration at any position of position X remains constant at any interval of time. This is called steady state. State is stable. This is a steady, this is a state, and this is steady. The concentration is not at all, it's varying. Okay, this is how. So next is we'll getting into this problem, right? So what he is saying is, first we will draw the diagram, then we'll getting into the solution for this one. So I will draw a, this is a rubber, or I will make it as gloves, and this is chemical methyl chloride, chloride, and this is your skin. Okay, so this is the concentration of methyl chloride here, and it is steadily it is decreasing. This is C1 and this is C2. So this is how we have made our problem very easy. Or to solve this one, we need to determine the J value. So J is equals to minus D into dc into dx. So we know why this a negative sign is there. Always the diffusion will occurs down the concentration of gradient. That's why we should mention that is negative value. So we know that the value of D. I will take one more page screen so that it will be easy. Okay, so difficult. So what is the C1 value? Maybe 0.44, right? C2 value it is 0.02, and D value 110 into 10 to the power of minus 8. Consider centimeter square by second. Yes. So better take this one. Yes. Gram per centimeter cube. Okay. Mm-hmm. 0.44, 0.02, 110 plus minus centimeter square per second. Yes. Gram per centimeter cube. Yes. So I will write one more time. C1.44 gram per centimeter cube. C2.02 gram per centimeter cube. Then D value is given as 110 into 10 to the power minus 8 centimeters square by second. So need to determine J value. So from the fifth first law, so consider we have as a steady state 110 minus 8. So write it this one. Okay. So we have C2 minus C1, X2 minus X1. So a thickness of gloss is point 2.02 centimeter. Okay, this is D value consider. So it is 110 into 10 to the minus 8. Then C2 value is point, this should be negative value, 0.02 minus point 0.4 x2 minus x1 should be equal to 0.02. Just calculate this value. Please let me know. And calculate the 0.02 minus 0.44 divided by 0.02 into 110. So that will be 2.310 10 to the power of minus 5. What will be the unit for this one? Gram per centimeter square per second. Right? Yes. That means for 1 second, this much quantity for 1 second per unit area of cross section. This much quantity of uh, butyl rubber is diffusing through the gloves. So from here we can calculate. We can say whether it is harmful or useful of making this much thickness of butyl rubber gloves. So if you are saying, like, if we are proposing that, like, okay, the methyl chloride is diffusing through the gloves with this period of time, then we need to increase the thickness here. If you increase the thickness of so for example, one more question that we can frame here. So if you increase the thickness by double, that is 2 times, so what will be the its diffusivity value? It will be half. Yes. So that will be 1.1 into 10 power of minus 5. Yes, the diffusivity value is reduced by its half if you increase the, because it is directly related to the thickness or diffusing distances. Okay. So we will be next jumping into the next problem here. Yes. So okay. The next problem is a fundamental problem. So in this one, rank the magnitude of a diffusion coefficient from the largest to smallest one. So we can add uh, two more elements. For example, nickel or aluminium in Fe at 700. So a nickel in Fe at 700 degrees Celsius. So if you want to calculate a D value, need to know the need to know three important. So this is di- uh, proportionality diffusivity value and activation energy and temperature. So from here, so D value, so diffusion coefficient value can be determined on the basis of activation energy. So as we know, on the basis of radius, atomic radius, we can say which one is having the highest activation energy and which one is having the lowest activation energy. 1 minute. I will tell the atomic radius of each element. Yes, we got it. Here it is there. Fe is having an atomic radius of here is iron, nickel, cobalt I have here. Yes, 156 it is picometer. What about nitrogen? 56. Chromium, aluminium I have right now. I'll rate it as aluminum as 118, cobalt I have copper, gallium, gold, yes, nickel 149 micrometer, chromium 166 micrometer. So we can say instead of diffusion coefficient value, here we are difficult to determine the diffusion coefficient value because we don't know value of D as well as Q value also. So we will change this question into the which one will diffuse this faster. Yes, on the basis of this atomic radius. Okay, so on the basis of this atomic radius in the iron, nitrogen diffusing faster since its atomic radius is smaller among all the things, whereas second number it goes to aluminium. All the three elements will do a substitutional diffusion because it is a very these atomic radius are very close to the iron, right? So that's why it will do a substitution, a diffusion coefficients, whereas all other nitrogen will give a sorry, interstitial, whereas all the three elements, that is chromium, aluminium and nickel, sorry for this one, so all the three elements will goes into the substitutional diffusion. Diffusion. So that's why as we increases the atomic radius, the diffusion, removing of a, uh, atom and a placing of this bigger atom is very difficult. See, here atom position is there. So there is a sufficient in more number of interstitial sites are available. Okay, here. So that's why the nitrogen we can diffuse very easily, whereas the other atoms should substitute these iron values, iron atoms should substituted with other elements. So if you increases the atomic radius, then the replacement of those, so if you remove this atom and again you need extra energy to fit that a larger atom into the sites because we have to push other atoms of iron in the larger distances, then only so diffusion will occur. That's why it requires more amount of energy for the higher atoms. That means a chromium is having a least diffusion value, whereas third position goes to nickel and fourth position goes to chromium. Okay, so this is all about the second question. The third question is compute the amount of hydrogen that passes per hour through a 6 mm thick sheet of a palladium having an area of cross section of 0.25 meter square at 600 degrees Celsius, assuming that a diffusion coefficient of 1.7 into 10 to the power minus 8 meter square per second, that, that the concentration at the high and low pressure side of the plate are 2 and 4 kg for hydrogen per meter cube of a palladium, and study that the steady condition has been attained. So I will draw first we have to draw a diagram. So this is at a higher pressure and this is at a lower pressure. So we have gradient of 4 kg as well as 2 kg of palladium. So given we will write it. D value is 1.7 into 10 to the power minus 8 meter square per second. C1 is 4 kg per meter cube. C2 is 2 kg per meter cube. So temperature is given as 600 degrees Celsius. That is not related to us. And the area is 0.25 meter square. So J is equals to minus D into C2 minus C1 divided by X2 minus X1. So here thickness is 6 mm. Yes. So substitute those value here and get the flux value. First, I'll give 2 minutes time. Okay. So right, we'll substitute the values. 1.7 into 10 to the power of minus 8. So what about C2 value? It is 2 kg and C1 value is 4 kg. Should be negative value. Here it is 6 mm is there. We need to convert into meters. 6 into 10 to the power of minus 3 meter. 6 into 10 to the power of minus 3 meters. So we'll get the value. We'll calculate it once more time. 1.7 into 2 divided by 6. It will be 0.5566 into 10 to the power of minus 5. This is kg per meter square per second that we got right now. But we need it in the form of per hour. Okay, first only per hour we need it. Then we need to convert this answer. This is not a complete answer for our question. So first we need to multiply with the area so that meter square will cancel out. 0.566 into 10 to the power of minus 5 into this area is 0.25, that will give rise to 0.1416. We got kg per second, we got it, but we need in the form of kg per hour. That's why we need to multiply this 0.1416 into 3600. This answer is, sorry, so this will be into 10 to the power of minus 5. I missed it here. This will be 5.10 into 10 to the power of minus 3 kg per hour, or 5.10 gram per hour. So these many grams of palladium is diffusing from this much thickness of sheet for 1 hour when we are maintaining the temperature of 600 degrees Celsius. Okay. So one question that I want to ask here, if you want to change, if you are changing this 600 degrees Celsius, for example, this 600 is changes to 700 degrees Celsius. So what will be this J value? Whether it is increases or decreases, please tell me. Think and tell me in the comment box section. I will give 1 minute of time. Okay, so I have given 2 minutes of time for you to think about this question. So, if you increases the temperature from 600 to 700 degrees Celsius, so this diffusivity value will changes. So, what the here the diffusivity value which is given here, it is 1.7 into 10 to the power minus 8 is for at 600 degrees Celsius. At 600 degrees Celsius, a D value is 1.7 into 10 to the power minus 8. Whereas if you increases the temperature, a D value changes to 2.5. Example, I'm just telling some example. So because the activation energy, thermal activation energy is increased, activation energy is increased, the D value is also should increase from the relation of D is equals to D naught into exponential of minus Q by RT, right? So if you increases the T value here, the D value should and must increase. That's why the diffusion it is also increased. Please tell me if it is 2.5, so what will be the J value? So what will be the J value? Yes. So just calculate for you your sake 2 into 2.5 divided by 6 into 10 to the power of minus 5. It is here it is given as 0.8 into 10 to the power of 0.833. Here it is given 0.55 into 10 to the power minus 5. But if you increases to 100 degrees Celsius, diffusivity value, the flux value is increases to 0.3% is increased. It is 0.833 into 10 to the power minus 5. So totally, so it is increases to 7.5 grams per hour. Right? So this is the question of this week. Fourth question is very interesting question. A thin sheet of an iron is in contact with the carburizing gas on the one side and the decarburizing gas on the other side at a temperature of 1000 degrees Celsius. Sketch the resultant carbon concentration profile when the steady state has been reached, assuming the surface concentration are maintained at zero point 0.5 as well as 1.4 degree weight percent of carbon. Yes, first we will do a first problem. So, as we say, there is a key word called as steady state. It's emphasized and we have to draw the sorry. Yes. Here it is at 1.4 and here it is 0.15. Since it is a steady state condition, it is straight line. As I said, if you consider any position here, 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 the concentration at any time it will be constant. Okay, so this is the profile. This is carburizing side. This is a decarburizing side. Okay, so this is decarburizing side. This is a profile for the. So next is what will be the. So I will add one more slide here. Insert a slide and I will make it as new slide here. So I will make it as new slide. Okay. So if we add the values, if DC increases from 2.5 to second, we will go second question. That is, if a DC increases from 2.5 into 10 to the power minus 11 meters square per second at 0.15. Okay, okay. To 7.7 into 10 to the power minus 11 meters square per second at 1 mole. What will be the quantitative relationship between the concentration gradient at the surfaces? So try to solve this question. I will also solve along with you guys. I will write it as on the D value. C1 is 1.4.15. 1 point of 1.4, and the DC value is, we have to write now, it's 0.15, and DC value it is 2.5, it's 7.5. 2.5 towards 0.15, 7.7. This is 7.7. 7.7 into 10 to the power minus 11. It's a 2.5. Yes, it's 2.5 into 10 to the power minus 11. So meter square per second. Meter square per second. Meter square per second. So since it's a flux is constant of 1 equal to J of 2, then it's high pressure side into dc dx. So d1 c1 and d2 x. So directly we can say, so what's the question he is asking? Okay, so what will be the quantitative relationship between the concentration gradient at the surfaces? Yeah, yes. We need to know the relative concentration. We have this is towards 1.4 side, and this is towards 0.15 towards. We have all both the diffusivity values. Okay, that is dc1 divided by dx towards 1.4 to the dc divided by dx towards 0.15, that is given as 2.5 into 10 to the power of minus 11 to the 7.7 into 10 to the power of minus 11. So you just tell me the answer. The answer is 0.32. 0.324. So, what is its significant? Yes, it indicates that the plate on the carburizing side, this is carburizing side and this is decarbonizing side. Okay, so one more time with a different ink, I will write it. This is carburizing side and this is decarbonizing side. Okay, so the rate of diffusion on the carburizing side is sorry, the concentration gradient on the carburizing side is greater lesser than 0.15 side. That's why it is diffusing like this. So diffusivity value is lesser. The atom is diffusing faster here and it is slower here because the diffusivity value are different. Okay. So this is all about today's session. So if you have any doubt, please let me know. So for we have 10 minutes of some time to to so we can explain, so we can discuss regarding with the Fick's law. He has considered a discrete atomic jump model. Discrete atomic model. That means, so when he is traveling from C1 to C2, he has considered this term as small entities, small planes. Yeah, yes, almost straight. The day I got right now. So, if you go atomistic level, the atom is jumping from right hand to right, left to right, and right to left. Then this is J plus, and this is J minus. But we are considering the unit cross section area. And we have concentration of atoms on the left side is n minus, and this is n plus, and the frequency with which it is diffusing from left to right is gamma minus, and the frequency is gamma plus. On the right to left is gamma plus. It's a jump frequency. That's jump frequency is nothing but the number of successful jump from one plane to another plane. Gamma is nothing but number of successful jump from ij. I plane to ith plane to jth plane. Okay. Sorry. The total number of jumps from plane 1 to plane 1 to plane 2 per unit time is given as total number of jumps from plane 1 to plane 2 per unit time is given as ni1 to gamma plus. Similarly, from plane 2 to plane 1 given as n2 gamma minus. The concentration is given as Ci1 to Ni plus divided by alpha. Why it is alpha? Sorry, what is alpha? Let know. 2 N2 into alpha. So alpha is, so this is concentration. C is we know that the moles to the volume. Volume, since we are considering the unit thickness T is equals to 1, then the volume is given as 1 into alpha. That means alpha. So that's why C1 and C2 are alpha. Okay. Sorry. Okay. So we have till here. So then to measure the flux across the plane P, measure the flux across the plane P. What is plane P? So, as I said, between the atoms, we are considering a random plane P. It's a reference plane. Like we need to observe only that plane that is related to others also. So you can observe here, here, somewhere else, but in the middle, we are measuring the flux here. So here J plus and this is J minus kind of thing. That means flux at plane P is given as J plus minus J minus because it is moving from left to right and right to left in opposite direction, then it is considered as J minus. Then we have we have already said this is n1 plus minus n2 minus 2. So we know n is equals to n1 plus dn dx alpha by 2 n2 minus dn dx alpha by 2. Yes, yes. Okay, so then we are proceeding ni1 into c alpha minus alpha square divided by 2 dc dx into c alpha plus alpha 2 to the divided by 2 into dc by dx. So we know j of p, substituting these two values into here in this equation, in this equation 1 considered. So then c alpha minus alpha square to the 2 dou c into dou x into gamma plus minus c alpha plus alpha square to the 2 dou c by dou x into gamma minus. Then we have minus alpha square gamma plus gamma minus divided by 2. Sorry, I have to make it here bracket dou c into dou x plus c alpha gamma plus minus gamma minus. So gamma plus equal to gamma minus equal to gamma. Then we have it as j of p into terms of minus alpha square gamma into bc into dx. This is nothing but minus d into dou c into dou x. Here, so next is we know d is equals to alpha square into gamma s. That means gamma s is equals to gamma divided by z. That is nothing but full jump. Okay, successful jump to coordination number. For a cubic system, if we consider this atom can jump towards this side, this, 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 up and down. So then the gamma s is equals to gamma divided by 6. And the d value is given as 1 by 6 into gamma into alpha square. So if gamma plus is not equal to gamma minus, then there is a term called as a drift comes into exist. Related to gamma plus minus gamma minus c into v. 1 minute. Stay in call. Okay. And the Here the drift velocity that is nothing but comes into exist alpha into gamma plus minus gamma minus. So if the drift velocity is present, that is gamma plus minus gamma minus, there is some velocity with which the atom are moving. Hence, there is a contribution of a Fickian term and the drift term to the diffusion flux. If gamma plus and gamma minus are not a zero, then the total flux is a summation of two contributions, nothing but Fickian, Fickian term and drift term. So Fickian term comes from concentration gradient, whereas a drift term comes under many other factors such as if you apply the magnetic field across the diffusion couple, it may enhance the diffusion flux, or there may be a lot of difference in the volume that may cause us a drift term. So these are all the other components that will affect the total flux. But in usual experimental case, this term we will neglect and we will consider only this Fickian term. So one more in this equation, one more kind of thing is being explained. Jp is equals to minus 1 by 2 alpha square gamma divided by 2 gamma divided by z summation of I equal to 1 to z cos square theta I dc into dx. Okay, so these are all the things that we have learned today. So thank you for your cooperation. Please let me know if you have any doubts and queries regarding with this thing.